Good evening, everybody. Thanks for being here so late. So Anthony's already set the scene for the first stars, and I thought I'd give you a good brief overview of where we stand in terms of what we know about the first stars and where's the future going to take us. So this picture is one of the only pictures that summarizes basically everything that we know about the universe, starting all the way from the Big Bang on the left to the present day, which is 13.78 billion years later and so on. In the very, very beginning, the universe was really, really hot. It was expanding really, really quickly. All of this stuff happened within the first second or so of the Big Bang, and that's what we think. We don't really know what exactly happened at that time. But at some point, the universe started to cool down a little bit, and things like electrons and protons and so on could recombine to form atoms for the first time. And after atoms could form, the stars could form, basically, which is this period marked by the first stars. We don't exactly know when that happened. We just know that it happened really, really early on in the history of the universe. And this is where the astrophysics, astronomy of stars and planets and galaxies really starts. Because in a way, everything that followed from these first stars. As you probably have seen already in the title, also from Anthony's talk, we haven't observed any of these stars ever. So in general, astronomy is a very observations-driven field. We observe something, and then we try to figure out what it means, what's the physics behind it, how can we use it, what can we learn more about it, or we predict something which we then want to go and observe. But we have never been able to observe any of these stars, like even after decades and decades of searches. So it still remains a very theory-driven, theoretical field, which is very, very rare in astronomy. Usually it's very observationally driven, but for the first stars, we have no observations yet. So why do we still care about them? These stars probably formed a very, very long time ago, but they are important for a lot of other things that we care about in astronomy and beyond. For example, which we have already mentioned quite a few times as well already tonight, Big Bang did not produce any heavy elements really. It only produced hydrogen, helium and lithium. So all of the elements that come after these three elements were basically produced in stars. But then the first stars that formed did not have access to these elements. So if we really want to understand how all of the different elements, which we call metals in astronomy all the time, were produced, how can we actually synthesize them in our laboratories on the Earth? What are the sort of formation processes? How do they react with other metals and other elements and so on? We really need to understand how they were formed in the first place, and that's where the first stars are the key for us to understand what really went on. They are also the building blocks of the first galaxies. So if you really want to understand how galaxies like the Milky Way formed, we try and go back in time to the first galaxies, which were basically built by these first stars, which now, thanks to the James Webb Space Telescope, maybe you've heard of it, it was launched a couple of years ago, we have been able to look much, much farther beyond than ever before. So this galaxy over here, it's a very tiny galaxy called JHGS Z14 something, is now the farthest known galaxy that we have discovered in the universe. This galaxy we are looking at a universe which was only 300 million years old. So this is as far as we have been able to push. And now we are starting to see galaxies at those sort of times. A couple of years ago, we always thought the first stars formed like 700, 800 million years after the Big Bang. But that's not true anymore, because we see galaxies already forming 300 million years after the Big Bang, which means that these stars formed even earlier than them. And potentially some of these galaxies contain or harbor these first stars. But it's really hard to be able to actually look at these galaxies on a star-by-star basis. They're very important for galactic archaeology. It's a term that Anthony already introduced, so it talks about the archaeology of the Milky Way itself, and trying to figure out how did the early Milky Way form, what were the first stars that were basically building the proto-Milky Way. And we think that the first stars in general were the ancestors of those sort of stars. So how those stars formed was really influenced by how the first stars formed in the first place. Here is an example of the most metal-poor star that we have known to date. There's a lot of stuff on this plot. All I want you to focus on is the atomic number. So iron is in particular the most important metal in stars that we care about. So if we are able to measure lesser and lesser amounts of iron in a particular star, it turns out to be very, very metal poor and usually very, very old as well, because as the universe has grown over time, stars have produced a lot of metals, but if you go far back in time, there were not enough metals in the first place. So you would see very less amounts of iron. For example, in this star, it only has 1/1,000,000th the amount of iron that we see in the sun. There's a very funny story about how this star was discovered. It was discovered by somebody who has never done observations ever. This was their first time observing with a telescope 8-9 years ago, and this was the first star they discovered. Finding these stars is like finding a needle in a haystack. Like Anthony said, Gaia has now looked at 2 billion stars. Do you know how many such stars we have which are so metal poor? Out of those 2 billion, less than 100. So it's like finding that one star that is so metal poor on your first night of observations is lucky. So this person who found this star has never done observations again. If you found the record-breaking star, you don't touch observations again. You do the theory.
How did you know it was real? I would consider it an observation error.
That was the first attempt. Like, I mean, in the first solar spectra, they thought maybe there is some problem or some error, but other people who had been looking for these stars, searching for them for lots and lots of years, were like, damn you, okay, this doesn't beginner's life. And a very recent area that has become really, really relevant for the first stars is something called gravitational waves. Einstein predicted gravitational waves in the, when Einstein was alive, so like back in the 1950s and 40s, but it was only in 2015 or so when we were actually able to detect the gravitational wave signature for the first time in the universe. So this happens when two black holes merge, for example. So I'm going to try and play a movie which basically tells you what this gravitational wave signal sounds like, because it's a sound, not a real video. If you have a pin drop silence and just listen to this chirp. Yep, that's exactly what it sounds like in real life. And this sound got 3 people the Nobel Prize in Physics in 2017. Usually, it takes ages for somebody to win a Nobel Prize. You do discovery like in 1990, you win a Nobel Prize in 2020. You have to be alive until then. It takes a lot of time to actually go to a Nobel. This happened in 2015, and they got the Nobel in 2017. It's the fastest Nobel in the history of Nobel Prizes in physics. And first stars are really important here because we do think that they produce the first black holes as well. And if those black holes merge, then that means that they would have given rise to a gravitational waves detection, which we could observe with the next generation of missions that the European Space Agency as well as NASA are planning, which is why this is a very exciting field nowadays that relates to the first stars. But what are the challenges in finding the first stars? Firstly, we think that these stars formed at a very, very early period. Right now we're talking about the first 100 or 200 million years since Big Bang. And that period remains inaccessible even with the most sensitive telescopes that we have. It is already very difficult to look at something which is 300 million years after the Big Bang, but going even farther back in time is really, really tricky. It requires at least $10 billion and a functioning US government. So that's a very big problem. We don't have access to telescopes or sensitivity enough that will actually take us to those times. Now, the second problem is, and I'll show you this a bit as well in the rest of the talk, that these stars we think were very, very massive. It was also one of the questions in the quiz. Typically, we think that these stars were 100 times as massive as the sun. If we were around a star that was 100 times as massive as the sun, we would not be alive. It's just too big of a star with a lot of energy, a lot of powerful radiation that planets like Earth cannot really sustain. But what also means with the mass of the star is that the age of the star is lower as the mass of the star increases. So the more massive the star, the shorter amount of time it lives for. So now imagine you are at a redshift or you are at a time when you cannot observe, and then these stars are massive, so they haven't survived for a very long time. So you have to be extremely, extremely lucky to actually catch up with these in action. Let's say you do that, but we don't know where to look for them. We have some ideas of where to look for them, but they are as good as anyone's guess in this way. And let's say we knew where to look for them, we still don't know how to identify them because we never observed any of them. If somebody was able to detect and convincingly show that there is a first star that they have found, discovered, whatever, this is again thought of as an area where you would probably get a Nobel Prize at some point in the future, provided you are alive. So these are the major challenges. Inaccessible with telescopes, very massive, so haven't looked for long. We do not know where to look for them, we do not know how to identify them. And this is sort of an area where we really have to push our understanding of physics and chemistry and so on to figure out how these stars formed in the first place. Which is both good and bad. It's good because it gets you to push your knowledge that we have collected over the last so many years and figure out where these stars would be and how to observe them. It's bad because we really have to push our physics, not all of which we really understand very well or are able to replicate in a computer that easily. So, the fundamental question is, when do stars really form? It's when gravity dominates all other forces. That's the main thing. So if gravity is able to win, it will be able to bring all of this gas of hydrogen and helium and metals and all sorts of things together, and it will be able to increase the density of the gas until a point where you reach nuclear fusion and then a star is born. But there is a huge range of physics from the time these clouds of gas start to come together because of gravity to the point where nuclear fusion starts and a star is born. Now, gravity is of course the most important thing, but it's not the only thing that exists in the universe when stars are forming in general. We require a lot of other physics and chemistry that goes along with it. So for example, hydrodynamics. This basically is the study of fluids. We treat gas as a fluid because that's the best approximation we have for astrophysics in astrophysics in general. So understanding how gas is moving around in the universe is very critical for us to understand which gas will form stars, which gas will not form stars, and so on. Which means solving the equations for hydrodynamics, which are exactly the same equations people use for climate modeling, ocean currents, turbulence, aerodynamics, and so on. But these are really complicated equations to solve, and it requires a lot of computing power to be able to actually understand how fluids interact with other fluids or how they basically will lead in space to the formation of stars. Chemistry is also really, really important in space. We have things like hydrogen, helium, other things as well. How the chemical state of the gas changes, for example, how does carbon and oxygen react to form CO2 or O2 or so on, is very critical when stars are forming. Because all of this chemistry dictates how hot the gas is going to be, and that matters a lot for the type and the masses of stars that we are going to form. Turbulence exists everywhere, as in aircrafts as well as in space. It is really, really challenging to model turbulence very well. Which is one of the reasons why, for example, even in climate modeling, our predictions are not as accurate as we would want them to be. It's the same thing in space as well. What nature does, we cannot really replicate to that level in our computers. Usually turbulence is quantified by a particular number. In the universe, that number is something like 1 billion. In computers, the most that we have been able to crank the number up to is 10,000. So this just tells you the sort of problems we have when we're trying to simulate or understand how the universe works in different aspects. Electromagnetism. The universe has lots of ions and electrons and so on. They are moving all around in the empty space. They will create an electric field, they will create a magnetic field. And all of these fields again matter a lot for how stars are going to form. And finally, radiation. So once we have some stars that are formed, these stars start to emit copious amounts of radiation, which influences everything around them, and then dictates how subsequent stars will form in a particular environment. So you need a concoction of all of these sort of different physical processes to be able to simulate how first stars will form. Now each of these processes has taken decades and decades of development, theoretical, numerical, all sorts of things, including experimental developments as well. And it's like people have spent their entire PhDs just trying to figure out one of these processes. So it's really, really complicated to mix and match all of them and put them in the same computer at the same time. Just to sort of show you, these are the physical processes. The other problem is the problem of scales. Universe or space in general is very, very empty. Like the typical densities that we're talking about in the universe are something like 10 to the power minus 24 grams per centimeter cube. It's really, really empty in a way. And gas has to increase almost more than 24 orders of magnitude in density to form a star. Now, capturing this entire scale is not possible for any simulation that we have right now. It's really, really difficult. But the reason it matters so much is because based on what density the gas is at, the temperature of the gas can be very different. I'm showing this in degrees Celsius. So like minus 260, usually gas can be very, very cold and very, very empty in the outer space. But as it increases its density, because gravity is acting, stars are about to form, the gas becomes really, really hot, from minus 260 degrees all the way to plus 1000 degrees Celsius or even more. So there is a huge range of temperature, a massive range in densities where gas has to actually overcome to form a star in the first place. So it's not an easy process, it takes a lot of time as well. Now imagine on this scale, I cannot even put the sun here. Now you know the answer for what the typical density of the sun is. It's like around 1 grams per centimeter cube. We don't even have that on this scale anymore. The sun is somewhere over here. So even after doing all of this work, we are not able to exactly reach where a star really forms. We have to stop somewhere, like computers cannot cope up with these sort of calculations. Okay, so these are the problems. Now what are we trying to do about them? We're trying to see where would the first stars really form. So here is a snapshot of dark matter in the early universe. So it's basically all of these purple features that you see is where dark matter, or we think dark matter has accumulated in the early universe. And that accumulation of dark matter is really important because of gravity, because dark matter brings all of hydrogen and helium with it together. So wherever you see nodes where dark matter is important or dense, that's where gas is also important and dense. And it's in these sort of nodules where if you keep on zooming in from like very, very large scales to somewhat smaller scales, this is where we think the first stars formed. Now, there are no galaxies yet. Today, when we see stars forming, we see stars forming in galaxies. At this epoch, there are no galaxies. So these are just structures of dark matter with some amount of hydrogen and helium that they have pulled apart with them, where the first stars are going to form. Now, trying to do this in a computer simulation, as I've shown you already, is quite expensive. Even on regular supercomputers all around the world, they can take up to 6 months to run. If you try to do this on a regular laptop, you can. You just have to wait for something like 140 years or so. So you need a lot of computing power to be able to get something reasonable, get something in some humanly possible amount of time. But once you have been able to get all the way to these scales where stars are forming, where the density of the gas is high enough, you can then start to ask the most important question next, which is how massive were the first stars really? And this is a big topic of research because mass is the most fundamental quantity we care about when it comes to stars. If you do not know the mass of the star, it's really, really hard to figure out its other properties. So mass is really, really fundamental. And we don't, because we have never observed any of these stars, we don't know their masses. So we really have to get it from our physics. So what you're going to see here are some movies which show different simulations. It doesn't matter which panel you look at. The important thing to look at is, as a function of time in years, how does the mass of the star grow? And this is in terms of the mass of the sun. And if I play the movie, you will see that one solar mass is somewhere over here. And these stars are already quite massive. It's even in the first 1,000 years, which is a very, very short period for a star's life, these stars grow to be very massive. Already something like 20 solar masses, 40, 60 solar masses or so. These are really, really massive stars. The most massive star that we've actually observed directly is in the imaginary clouds. It has a mass of something like 200 solar masses. It's the most massive star that we've ever known of. For these stars, forming 200 solar masses is very easy. It's not a very big problem. So these were really, really massive. And you can see how the different panels show the temperature of the gas here and the density. But what matters is they don't really grow very linearly. They grow very differently based on what physics or chemistry you are able to include or exclude in the different simulations and so on. So the predictions really vary all over the place. Some models suggest, oh, the masses are probably like 40 to 50 solar masses. Some go beyond 100 solar masses as well. There are even models that suggest some of these first stars were as massive as 1,000,000 times solar. Even if you're doing astronomy, you may not be used to hearing this, that the mass of a single star could be 1,000,000 times the mass of the sun. So basically the mass still remains very unconstrained. All we can say that is going to be really, really large, much, much larger than the sun itself. Another interesting thing about these stars is that they already begin nuclear fusion in their cores when they are growing. So if you think of a star like the sun, it grew first to the mass that it has now, and then it started nuclear fusion. Those two phases do not overlap. But for the first stars, we routinely see that those phases actually overlap. So that it's really even hard to define what is the mass of the first star in the first place. More problems. They also form very, very close to each other. So imagine if you have the distance between the sun and Saturn or Jupiter. Instead of Saturn or Jupiter, you put another star there. Like all this entire window that you see over here, all of the stars that form in here are closer than the closest star we have to the sun. The closest star to the sun is Proxima Centauri right now. It's like 1.3 parsecs away in some units. This distance is much less than that. So these stars come really, really close to each other, which is very interesting. But there is a huge diversity of these stars, depending on how you tune the parameters of your physics, and you can do different simulations and so on. Sometimes you form only one star, the star is represented by the dot over here. Sometimes you form multiple stars, like 10, 15 stars and so on. They're all really, really close to each other in very compact, various configurations and stuff. But they form in very few numbers. So if we're forming stars in the Milky Way today, we usually form from one given gas cloud like 100 or even thousands of stars. In these conditions, in the very early universe, we only form like a few of these stars, at most 10, at most 20 or so on. So which means not only were these stars very massive, they were not abundantly present all around. It was very difficult to create a lot of these stars from the same amount of gas. But we want to find them. So maybe some of these stars were low mass. If some of these stars had a mass similar to the mass of the sun, then they would have survived to the present day, and then we potentially could observe them. So is that possible? Sometimes it is possible. For example, what happens is, we form a lot of first stars, and because of dynamical interactions between all of these stars, some stars get ejected from their natal environment, and then they are freely floating in the space, and they remain low mass. Like the mass of this object over here is less than the mass of the sun. So sometimes you can form low mass stars, which can even harbor planets around them. So this whole question of the first planets. We want to understand how planets and the solar system like the Earth formed. We also need to understand how the first planets formed in the early universe, for that matter. So it is possible, but we don't know where to look for them. We don't know where they would be. They would be really, really faint, and possibly you won't be able to observe them. It's also possible to form first stars not so early, but later on as well. So, for example, instead of forming these stars just 100 million years after Big Bang, what if we formed them 1 billion years after the Big Bang? It is possible. Now, why does it matter? Because we can actually observe this epoch from our telescopes now. So if there were first stars that were forming 1 billion years after Big Bang, then we would be able to observe them, and then potentially be able to find them, maybe even Nobel Prize in the way as well. So where to look for them? Maybe in our own galaxy, as Anthony said, maybe we can look towards the center of our own galaxy, which should harbor some of these first stars. But the problem there is there are so many other stars in the way. It's really, really hard to disentangle all the stars we have in the center of the Milky Way and figure out if any of them was a first star. We can also look in the outskirts of the Milky Way, where some of these first stars might be present, especially if they are low mass, but the outskirts are really too faint. So here we have a problem of overcrowding, and here we are just too faint. So it remains a big challenge to see them. There was a recent tantalizing paper out talking about maybe they have seen signatures of the first stars in one of the most distant galaxies ever observed. So here is a galaxy which has some emission from carbon. So it's not a first star, it's not completely metal-free. But next to this galaxy over here, there is some emission from only helium. and we did not detect any amounts of heavy elements or metals or whatsoever, which usually we think is the telltale signature of a first star or first star cluster, because they should not have any metals in them. It remains debated, we don't really know what this object is, but if possible, maybe in the outskirts of the first galaxies is where you can still maybe find some of these first stars. But how to identify them? It requires even more work, particularly in terms of how we do our simulations. Because these stars are forming so close to each other so early on, and we have no observations, we really have to push our physics more. So, as I showed you, the problem of scales is a big problem for us. We're trying to overcome them, and the future lies in doing simulations on GPUs. Because on GPUs, we are able to really zoom in into these sort of regions that have never been accessible before on simulations that we have done with traditional CPUs, for example. So in a traditional CPU simulation, all the ones that I've showed you until now, we cannot resolve anything which is closer than Saturn is to the Sun. But in these sort of simulations, we can now resolve even things that are in between the Moon and the Earth. So that's a big difference. It's a factor of 5,000 more resolution, 5,000 more difference. It means a factor of a few orders of magnitude in density that we can follow and understand how these first stars are really forming. And that is important to figure out what should be their observational signatures, what should we really look for in our observations. So, where do we stand? First stars formed at a time that is inaccessible, even with the most sensitive telescopes, but maybe they continue to form at later times, and maybe there is some hope there. They were very massive, but maybe not all of them were as massive as what we have always thought about. Maybe they are hidden somewhere within our own galaxy, or they are available just waiting for us to observe the first galaxies, in the outskirts of the first galaxies and so on. Or we have to wait for black hole mergers, which will be detected in the next decade or so from the sort of new space missions that are coming up, and they will have some signatures of the first stars possibly. And the future for us in this area lies in doing simulations on GPUs, which are much faster, much better at doing some of these sort of problems in astronomy, to help us create realistic signatures of how the first stars should look like. So there is some hope. And I can end over here. Thank you.
Questions for Piyush?
Why do astronomers call every other element that is not helium or hydrogen a metal?
We are very simple people. I cannot remember more than two names of all the elements, to be very honest. I mean, if you, but I mean, to be serious, like the thing is, all the other elements are present in such minute quantities as compared to hydrogen and helium in the universe that, like traditionally, the belief for a very long time was that they are probably not, they still observe them a lot, but they should not contribute a lot to a lot of the physical processes that are going on that help us try and understand space. And then it was the problem of, okay, you observe some amount of oxygen here, some amount of carbon there, but how do you compare the two? And sort of coming up with a normalization scale where we just call everything as a heavy element sort of helps us understand, okay, how enriched a particular environment is, or how poor in metals and heavy elements a particular environment is. But it's more historical. There are astronomers nowadays who are looking at very specific elements that we have never even thought of before, like thorium or something else. So we are getting better and better at that, but as a whole community, we still prefer calling all of them metals and just clubbing them all together, giving the chemists a nightmare about how to do all the chemistry. Yeah, that's a very good question. Oh yeah. So the question was, we actually do not reach the densities where the sun is actually going to form. So how do we know what we are doing is correct? We take help of other observations that we have. For example, observations of, because we do have observation of gas at all of those densities as well. So we try and see when we observe gas at densities lower than what would actually form a star, what are its physical conditions like, what is its temperature like, how many metals or heavy elements does that gas have, and then try and reproduce those stages. So for example, we can observe all of this gas as well. This is all diffuse gas in the universe. And we can also, in many cases, measure the temperature of this gas. And then we can see whether what we are doing in terms of the models is able to explain this part of the gravity space that we can simulate well or not. That's one of the main things we can do. Our stars, of course, we don't have any of that, so it's purely dependent on our physics. If the physics is wrong, then yeah, we are definitely wrong. Although we hope that's not the case.
Yes, thank you. You mentioned gravitational waves. How do they indicate that the first stars?
That's a good question. So the question is, how are gravitational waves indicating the presence of our stars? So the idea is, with LISA, which is the next generation of space mission for gravitational waves detection, we are hopeful that it will be able to detect black hole mergers at very, very high redshifts. And if you are able to detect a black hole merger, it gives you very solid constraints on the masses of the black holes that are merging. And the first black holes that appear in the universe come from the first stars. So if we knew the masses of the first black holes that are merging that we can now detect, that immediately tells us that there should have been some first stars of a given mass for them to be able to form a black hole of the mass that we are able to now measure. And that's the connection that we have with gravitational waves. If this is realistic and it does happen, it will give us one of the most stringent constraints on what should be the masses of these first stars, which, as I said, is like the most fundamental thing we care about at this moment.
You mentioned in one of your simulations that nomad stars could be ejected and that they might have formed planets. But what do we know about protoplanetary disks with primordial chemistry? Can they even form planets?
Yeah, it's a very good question. Rizana is asking whether we can form planets out of just hydrogen and helium. And I should also let everybody know that Rizana is my student doing these things. So she's putting me on the spot on purpose, I think. It is difficult to form planets without any heavy elements present. The idea is that some of these stars, if they are so massive, right, like 100 solar masses or more, they would have survived only for 1 or 2 million years, whereas planet formation would take a little bit longer than that. So by the time these stars have already exploded as supernovae, for example, they have produced a lot of other heavy elements as well. It's the supernova ejecta from these sort of stars that can produce planets, and this has been shown very recently by a group. So basically what they're seeing is these stars explode in the first 1 or 2 million years, then they produce oxygen, carbon, all sorts of things, and then somewhere around from that material you can actually form planetary sized objects.
But those nomads, like lonely stars that got ejected, they wouldn't then be able
They are still enriched because they're not super far, like I mean even from the massive stars, like they're not that far in the end, so they still get polluted from the materials of the more massive stars that have exploded and energy.
So at a later stage they can still form a protoplanetary.
Yeah, that's the idea. And at lower metallicities, usually planets take longer to form. That's what I think.
We'll talk.
Okay, very eager question. I just want to add up, but then the question is, where do we draw the line? What is like a failed star, and where is planet? It's like, okay, I'm gonna take one sand dune, some like small piece of sand out of the pile when this thing stops in being a pile. So planets can be only hydrogen. If it's not enough to start fusion, so brown dwarf stars are considered to be stars. So they're like, I don't know, it's complicated.
Yeah, no, it is complicated. I mean, usually fusion is one very like physically motivated way to sort of make this boundary between what is a planet versus what is a star. Brown dwarfs do fall in the category of the stars, but there are also some planets that are really, really massive. I'm not really aware of if we need to redefine the definition of a planet or so on at this point, but there is some separation that we still see. I mean, from the simulations point of view, the most important thing is that we call something a planet if the mass of that object is less than the mass of the minimum ground rod that you would have. And if it remains that mass or less massive than that, then that's when we would call it as a planet.
Okay, let's thank Piyush again.